In this video in this series of videos actually, we'll talk about one of my favorite topics in organic chemistry, which is aromatic compounds. It's nothing like it sounds like. When you hear the word aromatic, you think a pleasant smell. Most aromatic compounds actually smell horrible. But the reason that they're called aromatic compounds is because, I guess historically, people identified them with very characteristic smells. In chemistry, or at least in organic chemistry, aromaticity, or something being aromatic, has a totally different definition which has nothing to do with smell. That's what we'll talk about in this video and some of the future videos. What makes something aromatic as defined by an organic chemist. Before we can do that, we're going to talk very briefly about how we name aromatic compounds, and then we'll talk about benzene itself, which is the characteristic prototypical aromatic compound. And finally, what does it mean to be aromatic, and what is the stability that's conferred on aromatic compounds? How does that work? So to start with, benzene is kind of the classic, most simple aromatic compound. It has a formula C6H6. It's defined by a six-membered ring with three double bonds. That's benzene, right? Various derivatives of benzene, like if you have a methyl on there, that's called toluene. If you have two methyls on there, it's called xylene. We'll talk about the different isomers of that in a second. We call it benzene is an aromatic compound. Anything that contains a benzene ring is going to be an aromatic compound. So how do we name these compounds? Before we talk about that, it's very important to appreciate the fact that aromatic rings are found throughout nature, and they're also found throughout lots of different drugs. Lipitor is one of the most best-selling drugs ever. It has 3 aromatic rings. Nexium and Prevacid are also very have sold a lot. Plavix, Zoloft. If you've heard of Zyprexa, any of these drugs, they notice how the aromatic ring or the benzene ring is shown in red in all these different drugs. It's very common in drugs. So we need to understand its properties to understand why perhaps it's so common in drugs. How do we name simpler organic compounds that contain benzene rings? Well, we name benzene as the parent name, and we name the group that's coming off of it. So this would be called chlorobenzene. This is called nitrobenzene. This is a 2-carbon chain, so we call it ethylbenzene. If there's one group, if it's a monosubstituted benzene, we don't have to specify the position, right? Okay, and I'm not going to worry about you knowing this exception, but if we have a really long chain that's longer than 6 carbons, now we name the benzene ring as a substituent, so that it's named as a phenyl group, PHENYL, so this would be called 1-phenyl heptane because the phenyl group is on carbon 1. Okay, so what you'll encounter more often than not are these common names, and the ones that I'd like you to know are essentially toluene, phenol, anisole, aniline, benzoic acid, and benzaldehyde. So you only need to know 6. Toluene is the one with a methyl, phenol has an OH, anisole is an O-methyl, aniline NH2, benzoic acid is a carboxylic acid, benzaldehyde is an aldehyde. That's pretty easy. Okay, so what about disubstituted alkenes? How do we name those? Well, let's look at some examples. So the common way to do this is to name things that are 2 carbons away from each other ortho. So this is an ortho arrangement of groups on a benzene ring. 3 carbons away is meta, 4 carbons away is para. If we go 5 carbons away, now it's closer to say 3, so then we're at meta again and ortho again. Knowing the common names, right, we could call this ortho nitro anisole, right, because the nitro group is ortho to the anisole. This would be called meta-bromo-toluene or para-chloro-benzaldehyde. The other way you can do this, which is a little bit more straightforward, is just count how many carbons away. So the parent name is one of those common names that we talked about. The nitro group is on carbon 2, so this would be 2-nitro-anisole, or the bromo group is 3 carbons away from the parent structure, so this would be 3-bromo-toluene, or 1, 2, 3, 4, 4-chlorobenzene. You'll see these ortho, meta, para terms and 2, 3, 4 used interchangeably. What if you have more than 2 groups? Well, then you just name the parent. So you pick whatever it gets the highest priority is going to be phenol, since it's one of those 6 that we learned. And then you just number to give the lowest total, the lowest numbering scheme overall, right? So this would be carbon 1, and then we just number 2, 3, 4, 5, 6. So this is 3,5-dibromo phenol. If you have different substituents, you want to list those in alphabetical order. I'm not going to go crazy with forcing you to name crazy aromatic compounds. Okay, so for example, this would be 5-bromo-2-chlorophenol, because you list the groups in alphabetical order, and you want to go in this direction, right, because this would be 2,5 instead of 3,6. So let's talk a little bit about the structure of benzene. Why is it interesting? Why are we talking about aromatic compounds? Well, the guy who discovered the structure of benzene, his name was Kekulé. He was German, and now he has his own stamp. What he proposed, which is the way that we're going to understand benzene, is that there's 2 resonance structures of benzene, which we talked about very briefly at the beginning of last term, right? You can show that these 2 carbons are double bonded to each other, or you can show that these 2 carbons are double bonded to each other. Remember that when you have 2 equally contributing resonance structures, then the resonance hybrid, which actually more accurately reflects the structure of benzene, is that it's 1/2 of this resonance structure and 1/2 of this resonance structure. So what does that mean? Well, it means that if you measure the bond distance, right, between the individual carbons, they all are the same. All the CC bond links are the same, and they're somewhere in between a carbon-carbon single bond and a carbon-carbon double bond. So one way we can represent this is that we have sort of half of a double bond here, and we have half of a bond here, and we have half of a bond here, and half of a bond here, yada, yada, yada. So the Kekulé structure, which you've probably seen me draw in class already, is that you just have a circle here, which indicates that there's equal bonding character throughout the ring. Every single carbon-carbon bond is a 1.5 bond. Every single carbon has a single bond and half of a double bond, because it's a mix of these 2 resonance structures. Okay, so remember that if something has resonance, that means that it's stable, right? So if we have an isolated double bond, like cyclohexene, we've already learned that if you treat a double bond with bromine, bromine's going to add across the double bond to give us these dibromide products, right? But if you take benzene and drop bromine into benzene, nothing happens. Why would that be? Well, maybe part of the explanation is that because of its resonance stability, it's lower in energy, so it's much less likely to undergo chemical reactions. So that's one explanation. So one thing about aromaticity that you want to keep in mind is that aromaticity equals an added stability. And it means that for the most part, these things are relatively unreactive. They don't react like normal double bonds do. They're lower in energy. They're less reactive. They're aromatic. Okay, so can we measure aromaticity? Of course we can. Just like in the previous videos when we were talking about conjugation, right? Conjugation, the stability associated with conjugation is measured by hydrogenation, right? So if we take cyclohexene and we hydrogenate it, we release 120 kilojoules per mole of energy, right? So it's an exothermic reaction. So if we had 3 double bonds, you might expect that we would release 360 kilojoules, which is, 3 times 120. But what we get out is 208 kilojoules per mole. So you can see the stability of aromaticity is huge. We're getting out like over 150 kilojoules per mole of energy, or we're lower in energy by 150 kilojoules per mole. We can hydrogenate benzene, but it requires very high temperatures and very high pressures. Benzene is extremely stable, and we can measure that stability through hydrogenation. Another way to picture this is that we would expect benzene, if they were acting as isolated double bonds, to release 360 kilojoules per mole of energy when we make cyclohexane. What we actually observe is only 208 kilojoules per mole is released. So the difference is what we're going to call aromaticity. It's the stability associated with having 3 double bonds in a ring that are conjugated with one another. It's a huge amount of stability that's conferred to benzene. Okay, so why? Why is benzene so stable? Of course, we have to go back to molecular orbital theory. Remember, when you combine pi bonds, when you combine p orbitals, they form pi bonds. And when you combine 2 p orbitals, right, you get 2 pi bonds, or you get 2 molecular orbitals. So you have 2 p orbitals. If we add them together, we get a pi bond, and we get an antibonding orbital. We get a bonding and an antibonding orbital. This one's lower in energy, this one's higher in energy. So for benzene, what are we doing? For benzene, let's think about it. We have 6 carbons. Each one is sp2 hybridized. So we have 6 p orbitals that we have to combine. So we need a molecular orbital representation of the combination of 6 p orbitals to make 6 molecular orbitals. So when we take 6 isolated p orbitals, that would be, they're not bonded to one another. This line represents the difference between bonding and non-bonding. But if we take all 6 p orbitals and they're all in phase with one another, there's a huge amount of stability associated with that, and we have 2 electrons in that. Each one of these p orbitals has 1 electron, and then we have 2 orbitals that contain 1 node. So we have 3 bonding molecular orbitals, but they're all bonding, they're all very stable. They're below this line that represents the difference between bonding and anti-bonding, and it's way more stable than if we had 3 isolated pi bonds would be somewhere in this range. So we have a lot more stability. That's why benzene is so stable, is because of molecular orbital theory. So to summarize, what I'd like you to know from this video is how to name mono-substituted benzenes, know the 6 common names that we talked about, know how to name disubstituted benzenes, namely ortho, meta, and para. Know that benzene is stable because it has 2 resonance structures, but the more technical reason is because of molecular orbital theory. It has nothing to do with the smell, but that stability associated with benzene and compounds that contain benzene rings is called aromaticity, and we're going to talk about that more later.